So we're very excited to have Robert Bindschadler with us today. He is an expert on Antarctic ice research, and he has led 17 expeditions over his 30-year career, and of course participated in several others to various glaciers and ice caps all around the world. So he's seen them all, and we get a chance to look at the ice sheets through his eyes, and let's take a look and ask him questions. And like we know, this is a very informal setup, so if you have a very interesting question, we encourage discussions even in the middle of the talk, and he's fine with that too. So thank you very much for coming and sharing your experience with us.
Yeah, thank you. It's a short commute for me. I just have to come from the other side of the building. So thank you. It's a pleasure to talk to sort of my home audience here. I go around the country and around the world a fair bit talking about ice sheets and what they're doing. This is certainly going to be more comfortable for me than sitting in one of the hearing rooms on Capitol Hill. I do some of that too. And I do want it to be informal, so as was said, if you have questions, wave your hand. If I don't see you, wave it more, and we'll answer. I'll try to get it answered as part of the talk. And we're going to have fun today because doing science is fun, and I think we need to remind ourselves of that. I'm going to start with actually, I saw Jeannie Allen in the audience, and many years ago she encouraged me when I was giving presentations to talk about myself at the beginning. I said, no, nobody cares about that. They care about the science results. Well, it turned out to be always a very, very popular aspect, and I do it more and more. And so for this Maniac talk, I'm encouraged to do that again. And I didn't have to have my arm twisted very hard because I think that is such an important part for most audiences. They want to connect with the person giving the presentation, and they don't connect best through equations and graphs and whatnot. They connect through the human element. So I dug into my family photo album, and I found this, which was the earliest picture I had of me on a glacier. And I'm the guy in the middle, that geeky-looking guy that's sort of halfway through college. And this is in the Canadian Rockies. This is Athabasca Glacier. And my mother on my right and my little brother on my left. And you can, I think, tell that I'm not thinking about glaciers there. Dad, get done with the photograph, But actually, that turned out to be quite a seminal trip for me because later on that day, we continued on up to Jasper National Park. And there's this mountain, it's not particularly prominent, but it's called Mount Temple, and it has this little glacier on it, and this beautiful little spot of white high elevation near the summit. And for some reason, Temple Glacier just stuck with me. And although when I was in college here, I was studying physics and astronomy, and I got degrees in both of those, but then I proceeded to worry my parents no end because I didn't go to graduate school. I didn't study any more physics. I didn't study any more astronomy. I actually worked construction for a while, and they thought they had just wasted thousands of dollars on my college education. Well, I kind of stumbled around. I was intrigued with the mountains, so I went to do a lot of mountain climbing. And then I realized I really liked the mountains that had snow and ice on them. And so I was in the Carnegie Library in Pittsburgh, Pennsylvania, my hometown, and I said, well, let me look up glaciers in the card catalog. So I found this tiny book called The Physics of Glaciers by Stan Patterson. I took it out, and I read it that night. And then I read all the format. I was just soaking this stuff up. And it turned out it was a graduate-level textbook in glaciology. And I said, well, that's kind of interesting. So much to my parents' relief, I found my way back to graduate school and got my degrees and all. And it's been fabulous for me ever since. Fast forward 30 years, here I am in Antarctica, one of the expeditions that I participated in. On the outskirts of McMurdo, roped up because we're doing some survival training, some crevasse rescue training. And the reason I show this picture actually is just as a backdrop to say that you really can't sort of tell what I'm thinking about there. I am thinking about glaciers at that point. But actually, I channel this guy. I don't look like this guy. I don't have his money. I don't have his fame. But darn it, I have some amazing adventures over all the times I've been to Antarctica. It has been absolutely fabulous. And it is an adventure every time. I don't have bad guys chasing me, Nazis and whatnot. But it is an adventure every single time that I go there. So especially when I talk to young kids, I tell them science is fun. And science can be an adventure. You don't have to go to Antarctica. I also channel this guy, Sherlock Holmes, because when I was young, what I loved to do was read mysteries. My sister's Nancy drew mysteries, actually, more than the Hardy Boys. But those two, that genre of mystery always appealed to me when I was young. And I tell kids, I'm still solving mysteries. I mean, you can call me a scientist, but I'm a detective. You know, you go out, you collect your evidence, you gather your clues, you have your hypotheses, and you find out what's going on. That's what science is. It's really that exciting. It's not something boring that we too often, I think, let ourselves be depicted as boring. It's not. It's really fun, and it's a thrill to do it. Just some other pictures of me in some of the other field expeditions I've led. So drive snow machines. This is called a theodolite. This is, just tell you, this is before GPS. This is when you got dropped off someplace and you didn't know exactly where you were, and you had to do sunshots to find out where you were. So it's a lot easier with GPS these days. But I've had some fun doing this. Okay, my message today is actually pretty simple. We've just experienced and observed the most dramatic decade for ice sheets that humans have ever witnessed on this planet. And a lot of questions are popping up as a result of that, and I'm going to sort of, that'll be sort of a backbone of what I'm talking about today. Here's the message. They're shrinking, and they're going to continue to shrink. And sea level is going to increase, and the rate of rise will probably increase because the rate of shrinkage of the ice sheets is going to increase. And when I'm pressed to give a number of how high sea level is going to be by the end of this century, it's 1 meter. I keep coming up with 1 meter. Not too many significant digits on that. Probably not even one significant digit on that. But, and I'll show you where that comes from. But that's sort of the important message to take away. And there's another important forward message, but I'm holding that back, and you'll get that a little bit later. And we're working hard on this. A lot of people. I don't know anybody in the field of glaciology focused on land ice, so not the sea ice, not the snow, not lake and river ice, but land ice, glaciers, ice sheets, that's not working on some aspect of this problem. We've got to get this issue resolved. We have to know how fast sea level is going to be rising in the near term. Just a couple comments about climate change. There aren't any skeptics here, are there? No, they wouldn't admit it. Okay, it's a fact. And it's pretty neat for science. I mean, big signal to noise. I mean, whether you're studying the atmosphere or the ocean or the ice or the vegetation, a lot's happening, and that's really fun. And again, that just sort of emphasizes the fun of it. Big signal to noise. Okay, that's the science, but it's not so neat for everybody else outside of the walls of Goddard because change is always stressful. Sometimes it's dangerous, often costly. But so that's what they're worried about. So while we're having our fun, they're worried about what's happening. So we really have a responsibility. I'm not going to dwell on this in this talk, but while we're having the fun, we also have to realize that we have a significant responsibility to inform the public. We are the people who know what's going on and have the best predictions of what's going to happen, and we have to get that word out there. Okay, why do ice sheets matter to more than just people who like to go to remote places and be cold and shovel snow all the time? It's because it affects sea level directly, unequivocally, and this is a graphic that was put together here quite a while ago that just illustrates all those red dots, all the places that are going to be inundated with just a 1 meter rise in sea level, just halfway up to my waist. All these areas will be flooded. It's a big area. Broken down by continent here, it's Asia gets it the worst. Think about Bangladesh, think about the Irrawaddy Delta. So whether you measure it in terms of area Asia gets it the worst. Whether you measure in terms of people, numbers of people who will be displaced, Asia really gets it badly. You know, over 100 million people will have to move in this century. Where are they going to go? And in terms of cost, and darn it, you know, it used to be that $1 trillion was a big number. Well, it's still a big number if anybody wants to write a check for that. But in terms of economics, Europe, you know, is going to get substantially impacted by this 1 meter rise in sea level. And this is just first order costs. I mean the secondary costs are just enormous. I'd like to put this picture of the Maldives there. It's an island nation in the Indian Ocean. You probably know that, of a little bit over 300,000 people. And two anecdotes about the Maldives. The president of the country held as a PR stunt a cabinet meeting underwater with all the cabinet ministers wearing scuba gear. This was around COP15, the Copenhagen Climate Change Conference, to emphasize the fate that his nation faces. 1 meter rise in sea level, Maldives is gone. It's gone, and it's going to disappear this century. The other thing he's doing is quite serious. He's going around to the presidents of countries around the world trying to buy enough real estate for a little bit over 300,000 people. He wants to move his whole country as a unit to preserve the cultural heritage and unity of that country. Hasn't been successful yet, but that's what he's doing. I mean, that's the front line of climate change, if you ask me. That's some real issues going on. So this is a global issue. Yeah.
How were the costs estimated, and why do you think it will cost Africa nothing if that happens?
This is more the economic value of the land that would be inundated. I think Africa actually doesn't lose very much land. So it's just based on that, just the economic value that is assigned through some means of an acre of land. That's what it comes from. Okay, so it's not human costs folded into that. So it really is a much extreme lower estimate, if you will. Okay, but thanks for that question. Okay, we can learn a little bit from the past, and these are sort of the primary lessons I think that we can draw from looking at paleoclimate data. Ice sheets shrink in a warmer climate. We have 1 million years of paleoclimate data that say that. Every time the Earth has gotten warmer, sea level's gone up, and ice sheets have shrunk. We know that. Sea level has gone up a lot faster than what it's been doing even this past century and even the past few decades. I'll show just a quick chart and run through that. Sea level has been higher in our past. We know that. And a lot of that's come from Greenland, but not all of it. So Antarctica is probably in play as well. And then I'll pick up on this final point that Tidewater glaciers, I'll describe those a little bit later. A few folks out there in the audience I know what they are. I think that gives us a view to what the future may hold of the ice sheets that are present right now on our planet. But we've never observed one of these ice sheet collapses. When sea level has risen very rapidly, we like to assign the term an ice sheet collapse. We've never witnessed one of those. We don't know what they look like, but we may be looking at the opening chapters of that. So just a graphic to back up that statement about every time the world has gotten warmer, ice sheets have shrunk. You line up a record that goes back 400,000 years. This is from ice core data in Antarctica. And you see the glacial and interglacial cycles where it gets warm and it gets cold and it gets warm and it gets cold and it gets warm and it gets cold. And it does that about every 100,000 years. And it takes, the warm period's about 10,000 years long and the cooling period is about 90,000 years long. So it goes through this sawtooth variation. It's done that for 1 million years and even longer. And then you line that up with sea level that has risen and fallen, risen and fallen. And there's just, I mean, it just hits you right in the face that those are correlated. World gets warmer, sea level goes up, ice sheets go down. Because that's the only place you can get so much water. The ice sheets have to go down. to raise sea level that much. You know, we're talking over 100 meters. Yeah?
What's the method for estimating the temperature from the cores in Antarctica?
It's isotopic ratios.
Isotopic ratios.
Yeah, yeah. So, sea level record. This is just the last 20-some thousand years ago. And sea level was low because the ice sheets were big at the end of the last ice age. Ice sheets shrunk, sea level went up, but not uniformly. There were episodes, we call them meltwater pulses, where they shrank considerably faster than what's happening right now. So, sea level right now, the rate of rise is about 3.1 millimeters per year. You can find numbers as high as 3.8 millimeters per year, but you cannot find a number as high as 30 to 50 millimeters per year unless you go back to historical evidence. This is from sedimentology, primarily some coral records. But it's solid evidence that ice sheets can shrink much faster than what they're doing right now. It's in our history. Yeah?
Yeah.
John?
You're showing that history, I mean, 90,000 years into a cooling age. I mean, think about what the cost would be to civilization, you know, if we went into a new ice age.
Yeah. Oh, I've thought about the cost. You think about the cost too, and everybody else think about the cost. That's good advice. Think about what that would do. So, I mean, that's sobering. Yeah.
3.1 millimeters per annum, but in 70 or 90 years it will be a meter.
That's right. So it's got to accelerate. Well, no, it won't be. So it has to accelerate in order to reach a meter. Very definitely. I'm getting more questions than I want to show slides, so I'm going to encourage more questions. This is just to say that Greenland didn't contribute the full 5 meters when sea level was 5 meters higher. They've done some modeling in it, and so Antarctica is probably in place. And I should say, most of you probably don't know that land ice on the planet, 90% of it is in the Antarctic ice sheet. 9% of it is in the Greenland ice sheet. You're good at math, so that's 99% are just in those two ice sheets. So all the other ice that maybe you're more familiar with, glaciers, small ice caps, that adds up to just 1%. So it really is about the ice sheets, what the ice sheets are going to do if we're talking about large increases in sea level. So, so the easy part of answering this question that people like to put is that, I've already said it a number of times, ice sheets are going to shrink in this warming world. The hard part is how much and how fast, and that's where the research is really going. Now, the IPCC addressed this in their last report, the fourth assessment report, and this is just from, they projected, you know, they summarize observations, that's all that stuff, and then they do their best at projecting what the future is going to be, and sea level is one of the issues that they address. And so you can find in their report estimates that by the year 2100, sea level is going to rise anywhere from this to this in the various scenarios that they investigate. However, that has a very heavy caveat put on it. I mean, the media jumped all over this. They said, oh, that's much lower than the previous report, so sea level isn't as big an issue as it was. But they needed to look beyond the numbers, and eventually the next week or so they did, and they read, oh, ice dynamics isn't included in that. Well, I mean, that's sort of like doing your family budget without accounting for your mortgage. That's, and they acknowledged that wasn't part of the calculation, but IPCC, and I discussed them at great length, but they did an honest job of saying what was included and what wasn't and coming up with the best numbers. Susan Solomon told me, I said, why did you put that table in there with these numbers that are so low when you know that the numbers are going to be higher and all you had was words that said, essentially, don't believe the numbers? And she said because the government's handed her this table on sea level and say, you will fill in numbers. So that's the backstory of that from Susan Solomon herself. Ice sheets. Ice sheet volume is pretty simple in its basics. 3 things you have to think about. One is accumulation. It snows on the ice sheets. That's why they're there. It makes it grow the more it snows. They melt, usually around the edges, during the summertime. That makes them shrink. And it flows. So that ice flows back into the ocean. That's another way the ice sheets shrink. So they grow through accumulation, they shrink through melting and ice flow. This bar chart here is just a very coarse view of Greenland, say in the last century. That accumulation, I have some numbers there, was about twice these two components of volume loss, but you can see that these two contribute to about the same loss as accumulation is gain. So it was in balance. We call it mass balance. So Greenland wasn't growing or shrinking. The Greenland ice sheet wasn't growing or shrinking through most of the last century. Okay, and then I put sea level change up there just so you have an equivalent scale. So this is what we think is going to be happening this century. Accumulation is going to grow by about 10%, and melting is going to increase by about 50%. So that's going to more than compensate for the growth. And we see that going on right now in Greenland with satellite observations. And ice flow is also going to increase. In some places, it's increasing a lot. And we don't have any good idea of how far it might go. That's the problem. That's what brings me into work every day. We don't know how far that's going to go. So when it really comes down to it, we have a good handle on accumulation, atmospheric dynamics, these climate models, and some of you in the audience are leaders in that. They do a pretty good job. Melting, I think also these models, the global circulation models, do a pretty good job of getting a numeric handle on how that's going to play out this century. But this one, this ice flow, we don't have a good handle on. The other two essentially depend on atmospheric dynamics predominantly. But this ice flow, it's really complicated. It's not just about the ice. It's what the atmosphere is doing, what the ocean is doing, as well as what the ice is doing. We're going to have a little skit up here to illustrate that in a little bit. So get yourself ready. I'm determined to get to that point. So that last message, ice flow will dominate the future rate of ice change. It's not so much knowing the accumulation. We've got a good enough handle on that, got a good enough handle on this. We don't have we don't have a handle at all on the ice flow. Okay, so that's where we are. Observations of the present. As I've already said this, we've already seen the most dramatic decade of ice sheet behavior. With rapid decrease, I'll show this, a rapid decrease in ice sheet mass loss. And faster flow in summer. So these are, I'll just illustrate each of these with a graphic here in a moment. Disintegrating ice shelves in the Antarctic Peninsula always grabs headlines. It's a big, big deal. And then rapid retreat, thinning, acceleration, they all tend to go together of outlet glaciers. So, okay, accelerating loss of Greenland ice. You can sort of pick whatever satellite you want. I've chosen data from the GRACE satellite here in this particular figure from the paper by Isabella Velliconi, because I think it shows best sort of the ice sheet breathing in the wintertime, if you will. The accumulation allows it to grow. And in the summertime, it gets warm, melts, it loses mass, so it's breathing out. And so you see this annual growth and shrinkage of the ice sheet. And if it was stable, that would just be going along here. But it's not. It's decreasing. So it's losing more in the summertime than it's gaining in the wintertime. And that's partly because the melting is increasing, but it's also partly because the ice flow is increasing. Both mass loss processes are more than compensating for the increase in winter accumulation. This is a famous plot. In glaciology, for too long, the media used to love to play one glaciologist against another. And every time there was another paper that came out that tried to measure the mass balance of the ice sheet, whether it's Greenland or Antarctica, those numbers never lined up with everybody else's paper. So they would have these knockdown, drag-out fights with the media loved to cover about, well, what is the number? And then it just led to this incredible confusion out there in the general, the rest of the world, and that we didn't know what we were talking about. Bob Thomas, I think, was actually the one who deserves the credit for this. he said, well, let's take all the publications that are out there that give a number on mass balance, whether they use satellite altimetry and the change in elevation, or whether they're using what we call mass in, mass out, which is measurements usually through interferometric SAR techniques of the flow rate by which ice is leaving the continent, and compare that with the accumulation rate of snowfall, or whether it just measures, like GRACE does, the mass and how that's changing. Totally independent techniques, completely independent data sets. And each of these colored boxes represents a paper by some set of authors using one of those sets of data over some time period. So he just arranged them in terms of the uncertainty and the time window. And voila, you know, everybody's been right. And so, but it really paints this fairly sobering picture again of an ice sheet that had been quite stable in terms of mass balance and in approximate mass equilibrium over the last century, suddenly losing more and more ice. So farther down here is the rate of ice loss, and we're headed down that way. Antarctica, 10 times the size, but essentially the same picture. So these really were compelling illustrations of what's happening in the first part of this century, and disturbing in terms of where this arrow goes. Do you extrapolate the first derivative or the second derivative or the third derivative? People have done all of those, and you can get some really big numbers. The melt extent is increasing in Greenland. There's some pretty old graphics, but there are better ones to support the statement that overall the melt that is concentrated around the lower elevations, margins of the ice sheet in summertime, is increasing. You have a lot of variability, yes, but there's a definite trend towards an increasing area of surface melt. And there are experts here that study that a lot more carefully than I. I mentioned the Antarctic ice shelves. These are in the peninsula. The ones that are disintegrating are in the peninsula here. And again, they make headlines, and some other people here are studying these quite carefully. Here's the important thing. They take thousands of years to form. They form because snow accumulates on these glaciers in the sort of the mountainous spine of the Antarctic Peninsula and slowly flows out into the ocean, but at rates that exceed the melt. So gradually, and I do mean gradually, thousands of years, you get this big plate of floating ice. Well, these things have been observed by satellites to disintegrate in weeks. You know, the time scale difference is just mind-boggling. These things rapidly disintegrate. That's not natural variability. Those ice sheets, or those ice shelves, this is the floating bit, this sort of featureless looking area, they aren't coming back anytime soon. It takes thousands of years for them to come back. And Chris Schumann, I don't know if you're here. Yeah, he's in the back. He's been studying this quite extensively. Talk to him, he can give you all the details. But I love this picture of where the Crane Glacier used to be, because it's not just about the ice shelves. My concern is sea level, right? That's the drum I'm beating here. And an ice shelf is already floating, so you can get rid of the ice shelf and you don't change sea level at all. But those glaciers that fed the ice shelf, they also are responding to the loss of the ice shelf is down here and it's kind of disappeared. But this glacier, that's grounded ice, and that's been thinning really rapidly. And he's got some compelling illustrations of that. I just grabbed one from something he loaned me to illustrate this. So what's going on with the glaciers, that concerns people who are concerned about sea level. And this is just an earlier graphic that says that the Crane Glacier is, I didn't even mark it, it's up in there. No, I'm sorry, it is, it's here. It accelerated, not just as it thinning, but it accelerates. And those two things tend to go together. They go much faster and they thin as a result because it has to supply that extra ice. And it doesn't just accelerate a little bit, it accelerates a lot. It really slams its foot down on the throttle and accelerates by factors of 4 and 5 in 2 years. Now, when I was in graduate school, you know, we were told that glaciers can't do that. But but we've seen it. We've seen it. We've measured it. So we're rewriting the glaciological textbooks. Now, this is not happening everywhere. What I just showed you is happening over there in the peninsula. This part of Antarctica is another place. The colors here represent change in elevation. So it doesn't matter how you measure this. You see these massive signals. This is an area where my own field work has taken me in West Antarctica. Also in the East Antarctic, there are some places where this is going on. Around the margin of Greenland, it's going on. So it's around the margins, but not everywhere around the margins. So again, when you get back to the sort of this concept of detectives and gathering clues, that's important. Generally, it's the deepest, fastest glaciers that are responding in the most dramatic ways. These are the ones that are really lighting up the billboard here. And that's important. And I'll try to connect some comments I'll make later with that fact. And again, the numbers, the numbers are just huge. I mean, like I said, I was taught ice sheets can't do this, but they're doing it. You know, changes of 80% increase in velocity, that was about over a decade. Some of these numbers are sort of half-decadal changes. Jakobshavn sped up 95% and averaged over 10 years. This one did this in less than 5. Big numbers, big changes. And this is Jakobshavn. With that thinning came dramatic retreat. It retreated 10 kilometers in 50 years from the middle of the 1800s to the turn of that century. Another 10 kilometers took about 60 years. There was a still stand. There was sort of a brief cooling period. But that last 10-kilometer retreat, an order of magnitude faster. So, big stuff. Why? Okay, this is where I like to pause. Glaciologists are not allowed to respond. Why? One-word answer. What's driving all of this? I have to speak up. Be bold. Here. Close. Oh, come on. Every other audience has got it.
Political correctness.
We do. Now, culprit is? Somebody's probably said, I'm hearing a lot of murmurs, but you're timid, as scientists always are. Water! Water! Water's doing it all. And ice sheets hate water. So this is the 4-word mantra I want you to leave here with. Ice sheets hate water. Impress your friends and neighbors, because they will be puzzled by this, as I'm reading some expressions here as you are. This is so weird. Ice sheets are made of water, but water is public enemy number 1 for an ice sheet. And at this, my daughter drew this, so I have to wear the T-shirt. If I had a poster, I'd just put it up there on the side. I hope this doesn't. Okay, ice sheets hate water. If you look at me, that's gonna be driven deeper and deeper. Okay, now why? I mean, I told you what the observations were. Why do I say water is the culprit here? Water acting as a lubricant. This picture is iconic in glaciology. And I go to a glaciology talk, I show that picture, I don't have to say anything. They know what I'm talking about. This is one of these big meltwater streams are on the margin of Greenland. A lot of melt. Big lakes, those lakes drain, big rivers, and it finds cracks and in the ice, plunges down in them, makes what's called a moulin, glacier mill. And crazy spelunkers have tried to go down there, follow how far they go. We think they go all the way down to the base of the ice sheet. No spelunker has successfully gotten down to the base of the ice sheet. They've gotten pretty far. But the reason we think it gets down to the base are these measurements that Jay Zwally took quite a long time ago and published in Science, and which showed that, I won't go through details here, but the message here is that when it melts a lot, the glacier goes faster, the ice sheet goes faster. So it's acting as a lubricant, and it has to be getting down to the base. And we see evidence of it, of increased discharge at the end. So it's acting as a lubricant because friction between the ice and the bed does control how fast the ice can flow. So if you decrease that friction, it flows faster. Water is the result. You get more water, the more melt you get at the surface. This water is getting all the way through. A kilometer of ice, 1,000 meters of ice, it can find its way through. I talked about disintegrating ice shelves. Water is acting as a wedge. This is a higher resolution, this is MODIS data. And you can see that the process with a few snapshots there of what's happening. And you see all those little dark blue patches. Those are lakes. And the tops of water-filled crevasses. And what's really nice is that final one, it kind of changes color to this powdery blue. That's the inside of the ice shelf. What's happening is, we think, is that, okay, you have some crevasses, you have water, the water sits in those crevasses. These ones don't go all the way through initially. But in a warm summer, which is when this thing happens, it fills up with water. Now, okay, put your physics hat on. Down here at the tip of the crevasse, at its base, the ice is trying to squeeze that sucker shut, okay, just through pressure. And the water is trying to squeeze that thing open, trying to push it open. And if this crevasse is filled with water all the way to the top, what's heavier, water or ice? Water. Hey, everybody got that one right. So water wins, and as long as you keep that head to the top, the crevasse goes down. And if you have an excess of water to keep that crevasse full, then it will continue to go deeper. And it won't stop. I mean, there's absolutely no reason why that's going to stop. It will go all the way down until there's no more ice to go through. And so what you have done effectively is taken that ice shelf and just chopped it up into tall, thin blocks that then kind of fall over. They don't want to be sitting in the ocean as tall, thin blocks. They want to be wide, flat blocks, shallow blocks, thin blocks. So that's what happens there. It looks like it just explodes out into the ocean, but what's actually going on is these tall, thin blocks, these dominoes, if you will, are just pushing their neighbor out. So it just pushes itself all the way out farther into the ocean, and we get a snapshot of that. So water acting like a wedge. Okay, and so as I said, after that happens, this is pulling the cork out of the bottle and those glaciers speed up. This one's getting a little bit more complicated. This is a really nice paper by Dave Holland. He used, his data source for a lot of this was fishery information. The Greenlanders have an extensive fishery industry, and they're taking measurements of the temperature of the ocean water, both at surface and at depth, although here he's showing at depth. All the time, because whether it's cold water or cooler water or warmer water affects what type of fish are there and where they are. So they're monitoring that all the time. He used that data, and this is just a sequence time series year by year, starting in 1991, 92, 93, and the colors are the temperature. Blue's cool, red's warm. And you can see, so in here, there's this finger of warm water working its way up the southwest coast of Greenland. It arrives at that star in 1997. That star is the Jakobshavn ice stream, that big glacier, that one that was retreating so rapidly in the first part of the century. And that retreat and thinning and acceleration of that ice stream, that outlet glacier, started in 1997. At the same time that warm water arrived in the fjord. So it's circumstantial evidence, but again, pretty strong in the court of science, I'd say, that warm water is responsible for that reaction of the glacier. Its acceleration, its thinning, its retreat. So we see that in Greenland. Now we're going to get to the fun part. This is Antarctica. So that was water acting as a heater. This is a cartoon of kind of shows the same type of process in the Antarctic context. And this is where the fun starts. Because I'm going to build a model. and I need a few volunteers. I can do it in PowerPoint, but that's really boring. So here it is. Here it is. So we're gonna build our model up here. And so I need some volunteers. I need 6 volunteers. And so I've given them different roles. I need somebody to play the atmosphere. Talk stops here if I don't get 6 volunteers. Okay, come on up. And we'll put you over there. I need somebody to play the innocent bystander, the cold water. Well, come on down. I have props too. I really do. Now he's cold water, so I'm giving him a nice blue coat to wear. That's right. He would have been a natural. Well, I can. And then, who else do I need? I need, deep warm water. I need the villain. Okay, come on down. For you, you're warm water, so I have something red. The only thing red I had in my office was this big parka. So you'll be really warm by the time we get to it. And go over there by a cold water. Okay, continental shelf, the accomplice. Just somebody with long arms. Bob, are you standing up? You want to be the continental shelf?
Sure. What do you need?
I need you. That'll teach you for coming. So sit your Oh. Ooh, I never. Yes. Ice shelf. I need the tragic heroine. All right. Thank you. And then I need the glacier, the ice sheet, the big roll. I will intimidate you by saying that the second to last person who played this role for me was Al Gore. I had him dressed up in a bathrobe. And the person who played warm water, go ahead and put that on. So we know that you are the icy ice sheet. The last person to play warm water was Ted Turner. So this is distinguished company have humored me here. All the rest of you are the victim. You are the global ocean. Okay, so nobody gets away. Okay, so let's build our model. I want to start with the atmosphere. Okay, you start here. And then 2 ocean people come over. I'm actually going to get a chair. Okay, I'm going to get a chair. Just because Ted Turner had to, no, that's not for you, it's for that. Circumpolar, you're lower down. Okay, the only thing I know about polar oceanography is that it's 3 layers. It's cold on the top, warm in the middle, and cold on the bottom. Tropical oceans are warm on top and cold on the bottom, 2 layers. Polar oceans, 3 layers. So we have 2 layers. You're the surface water. Because you are surface, just hold your arms out over top of the intermediate depth warm water. This is my polar ocean model. Okay, continental shelf. Okay, move off to that side. We'll give the continental shelf some room. Just put your arms out. Okay, question again for the audience. Continental shelf is tilted at the edge of Antarctica. Which way is it tilted? Down towards the ice sheet or down towards the ocean? Down towards the ice sheet because of all the weight. So you tilt that way. That's all you need to do. Yep. And we have the ice shelf. The ice shelf is really key here. And the way you play the ice shelf is just put your arms apart like that. And if you really want to get into it, you can go like that because you are holding the ice sheet back. Okay? Okay. And you are the ice sheet and you're just there.
Cool.
Okay. This is our model. The continental shelf separates all this heat in the ocean from the ice sheet that hates all that heat. Okay? This is the situation. Now, in order to spin up this model, what's actually been happening is that the planet's warming. Have you heard? But Antarctica is not warming up as rapidly. Forget about the peninsula, that is. But all the rest, it's keeping itself cooler. Temperature gradient, pressure gradient. So the winds around Antarctica are increasing in speed. That's been measured. The way you're going to simulate that is just flap your arms. Now what happens? The surface water gets dragged around by the wind. Okay? Now we're in the southern hemisphere. The Coriolis effect is to steer things to the left. So because you've got Antarctica here, everybody has a map of well, I won't go into that. It goes this way. And so it's steering that surface water to the left means it's away from the continent. So you go away from the continent when the winds increase. Okay, we're just getting our rolls down. Now, if he goes away, the ocean, right? Deep water gets upwelled. So it rises. Ah, excellent. On cue. How sweet. But he's a heavy guy. He's a hot guy, but he's a heavy guy. And so he gets up onto the continental shelf because he's hovering right underneath, right at that lip. So we have our tilt here. You're heavy. So which way do you go? You arrive here, and you go this way. Right? You're just heavy. You just follow his slope. He's giving you a nice slope. You're going the right way. Whoa, hot water has arrived underneath the ice shelf. Because again, he's a low guy, but he's a hot guy. So you thin. And when she thins, you accelerate, and you only have one way to flow. You flow that way. So, places everybody. And what happens when the ice sheet goes into the ocean? You, global ocean, rise. Okay? Okay. This is my model. Hey, I used to be a decent modeler. Okay, we're going to start it. Okay, winds increase. Okay, you steer away, away from the continent. Warm water rises. You go down. The ice shelf thins, and the ice sheet flows into the ocean, and you rise. Thank you very much. Thank you very much. That's all you need to. Thank you. One of the best models I've ever written. Okay, thanks. Okay, where do we go from here? You just learned a lot of glaciology. It's a complex system, and it's that strongly linked. I actually wrote that up in words in a proposal, and it got funded. So that's been the work we've been pursuing for quite a number of years on the Pine Island ice shelf. So water's darker side. If you're an ice sheet, you hate water for a whole bunch of reasons. I didn't even talk about this first one, the fact that it darkens the surface and increases the amount of radiation absorbed. But I did talk about lubricating the bed, and I talked about the hydrofracturing, the water acting as a wedge, and we just acted out this melting fluid. Actually, let me go back to the cartoon so you see. So now you can understand this. Here's our circumpolar deep water being brought up onto the continental shelf, getting underneath the ice shelf and melting that on its underside and thinning that, and away the glacier goes. So that's what we just witnessed. So how are we going to improve our understanding here? I mean, that's a hypothesis, and actually we have measurements to support most of those linkages. So we need field studies. We need some analog studies. I'll touch on them just briefly in the few minutes I have left. We need more field studies. I mean, there just is no substitute for field studies. We need numerical models that really wrap this together in a credible, predictive way that validate the measurements that we're collecting. And I think we need yet more field studies. That's the thing that we're really missing, because all of that, most of that action is happening where satellites can't see it. That's the tough part. So there's really no direct substitute. Analog studies, this is just an illustration of what some glaciers are doing. This is a Tidewater glacier. So it's coming out of the mountains. And in 1941, Muir Glacier came pretty far down in its fjord. And, but it's not there now. It's retreated a long ways. This is because this is a mountain glacier or a glacier that is grounded in its accumulation area, and then goes down, fills a fjord where the bed is below sea level. We call that Tidewater Glacier. And so I think we're going to be seeing this. I think we are seeing this numerous places around the ice sheets right now. And so this is looking at what's happened in Alaska. Why does Norway have all its fjords? Because all those Tidewater glaciers have retreated dramatically. The margin of the ice sheets are going to be looking more and more like that. Just in cartoon form, this is what's going on. This glacier comes out of the mountains. It erodes this soon-to-be beautiful fjord, and it piles up all that morainic material that it's been eroding up on this push moraine. So the terminus sits on the push moraine, mostly out of the deeper water, certainly. It can't advance very rapidly because it gets into deep water and retreats back. It can advance, but only at the rate it can push this moraine out. So it has something to sit on that leaves it in shallow water. And if it retreats back into deeper water. Doesn't like that. The calving rate increases dramatically. It continues to retreat, and it will continue to retreat unless it finds some other little rise to sit on. It will continue to retreat until it goes all the way out of the deep water and sits in water perhaps as shallow as this moraine. That's the drastic retreat of a tidewater glacier, and we see that again and again. This is not a gradual process. I thought I'd show you just a couple of videos because I had them, and they're kind of neat. The calving terminus of an outlet glacier, an ice sheet outlet glacier. These are big blocks that you probably see about 10 kilometers across the screen there. The one I like even better is this next one. I think these photos were taken about every minute or so and put together as a time lapse. Let's see if we get this one going. Did it advance to the next one? Okay, here's the next one. You see a block about the size of this building calve up. And remember that this is floating ice, so you only see the top 10%. So this is really thick ice. And because of that, it may melt on the surface and erode on the surface, but you have all of that ice underneath that actually now is not happy being submerged because it lost its 10% that's supposed to be above the surface. So it actually calves up this way. So that's why it's dangerous to be in those kinds of areas. This is the classic view of a tidewater glacier. This is Columbia Glacier in southeast Alaska. There's a shallow moraine out here where it was in 1980. In fact, it was out there for 100 years. And then it lost its grip on that, went into deep water, and in 20 years retreated 20 kilometers back to this point. It's continuing to retreat. It will retreat all the way back to here because that's where the bed finally gets up out above sea level. So we are monitoring that process. It's slowed down at the bend. The reason I show this picture is that this is taken from Google Earth. And this is the margin of the Greenland ice sheet. And this is Helheim Glacier. And it has visually the same characteristics. There is a shallow shoal right underneath that, the old moraine where it was pushing material out. It's lying underneath that. It's white here because that's all this brash ice, these broken up icebergs. Why are they there and not as thick out there? Because they're so big. They can't get over that shallow moraine. That's essentially a gate that keeps them locked up in there. But both of these are tidewater glaciers in drastic retreat mode. It's going on, and you can go to Google Earth and you can scroll around the margin of the Greenland ice sheet. Now that you know what to look for, you can see that in a bunch of places. That ice sheet's in trouble. So let's go back to this chart where the IPCC did what they could, but threw some caveats on that. And through various types of analyses, mostly analog studies, semi-empirical stuff, people have taken whacks at trying to include ice dynamics. And they end up with estimates up there. And there's about 3 times as many estimates now. And they're all up there. And 1 meter is always within the range that is predicted. Sometimes it's quite a bit higher. We think 2 meters is probably the ceiling for reasons that I won't go into right now. But that's probably where we're going to end up this century.
That's the ceiling without the West Antarctic.
The reason I call that a ceiling is that paper by Pfeffer, the green one, the approach he took was that we've seen some glaciers do some pretty dramatic things. Let's let more glaciers around the ice sheets do that dramatic thing. How fast can the ice come out of the ice sheet? And he ended up with numbers in that range. Then he said, well, let's make glaciers do even more dramatic things that we haven't seen yet. And that's how we ended up at 2 meters. So that requires some outlet glaciers to be even more dramatic than what's been observed yet. So most scientists aren't too comfortable going there. Yeah, Molly.
That's the 2100, right?
That's right.
You open, because whatever we do about this now.
Time doesn't stop here, does it? It keeps going here.
If you think about your planning horizon, 2100 is not actually that far away.
Yeah, I mean, a lot of people's attention span, sort of stops right there. Sort of Capitol Hill stops right there, and people with kids that, maybe stop there, and people that think their kids are going to have kids, they start thinking out here, and it goes farther and farther out. So you're absolutely right that we sometimes get too focused on 2100, but that is just the beginning. This is, I don't have time to talk about it. This is another important aspect that we don't often fully explore, and this is all the sea level numbers I've talked to up to this point are global averages. Well, okay, some people are going to see that, but most people won't see that. Some people will be above that, and some people will be below that. And so we call it fingerprinting the pattern of sea level change over the global ocean, and just expressing the non-uniformity of it. And what that mostly depends on is where that ice that's added to the ocean comes from. If it comes from Greenland, I mean, where you want to be is right next to the ice sheet that loses that mass, because it lost mass, and it actually is, crustally, it's going to rebound, and your local sea level is likely going to go down. It's going to go up for everybody else, and they have to, soak up a little bit more because the average is what it is. But if it comes from Greenland, far away, sort of this far field effect, they'll feel higher than average increases in sea level. If it comes from Antarctica, same thing. Around Antarctica, you're likely going to see very modest sea level rise, or perhaps even fall, but everybody else is going to get above average. And if it comes from glaciers and ice caps, which are primarily in the Andes and the North American high Arctic, again, a different fingerprint. So people are taking predictions. Sophie Nowicki, I know, is back there. She's working with modelers that have this kind of modeling capability, and supplying them with different source locations for different amounts of ice on different timescales, and looking at what the regional effect is going to be. Because as soon as we get people to finally understand the global average sea level is going to increase, they're going to want to know, well, how much is it going to increase on my coast? So we're working on that. Okay, this can be often taken as a depressing talk. It's not how I mean it, but so let me emphasize some good news. This actually is one of the easiest things about climate change to adapt to, because it's not going to happen overnight. I realized that after I scared a school audience, kids. They thought, they went home and they said, it's going to flood tomorrow. So no, it's not that bad. It's going to be gradual, but it is going to happen. I mean, what we have to do is accept that it is going to happen. Then we can adapt into this quite gracefully. Don't build the next high-rise right on the shore where the existing one is. Force them to go back. Just common sense, but often it's not compelling enough. But once we accept the fact that this is going to happen, we can adapt to it. Projections, there are a number of groups. I lead one here, and there are some others that are trying to do the best job we can of projecting future sea level. And we're getting better at that. This is just a number I pulled completely out of the air. I think we can probably reduce our uncertainty by about a factor of 2 every decade. This is hard stuff. We don't even know the processes all that well. We know them enough that I can put them on PowerPoint slides, but we don't know them well enough that people can put them in credible predictive models right now. And that's where we have to get. And it's a good investment, because if we don't do it, we really don't know what sea level is going to be doing, and then we cannot adapt to it intelligently. And we're smarter than this. We really shouldn't be sticking our heads in the sand and ignoring this problem. This is an easy one to address.
On that first point, maybe I just challenge it a little bit because these things are pretty nonlinear, right? So,
yeah.
You know, even if it may take 8 centuries for all of Greenland to disappear, like we saw with the sea ice in 2007, that had a big drop and then sort of partly recovered. Why couldn't, say, Greenland or the Palmer Peninsula, as we saw with Larsen A and Larsen B, have an episodic disastrous change within a decade?
It's a great question. And it really leads back to what I was mentioning before about that ceiling being 2 meters. You still have to get the ice out of the ice sheet. And it's deeply incised around the edges, and those incisions define these outlet glaciers. And those are the pipes. You know, there aren't any extra pipes to get it out faster. There's got to go through those pipes. And so that I think is a reasonable approach, and why I like Tad's approach to trying to find how fast can it come out. Even if you lubricate the whole thing, it still has to come through those pipes. So there are some breaks and some limits on the system. But you're right, that has a scary episodic character to it, and nonlinear character that we don't understand. Absolutely. Summary. Okay, I hope you know this now. Sea level is going to continue to go up. Ice sheets are going to continue to shrink because it's going to continue to get warmer. And it's likely going to accelerate because ice sheets hate water. We'll get to that. The best estimate, and really the number that a lot of us go around touting, is this 1 meter. I mean, it's not, we don't, like I said, have many significant digits there. But it's a pretty good number that keeps popping up from a variety of approaches. Let me just get through this, and I'll take your question first. And I tried to illustrate what the 3 key processes are. None of these, again, were on the radar when I was in graduate school. None of them were on the radar even 10 years ago. I think it was Wally's paper that came out that sort of put the first one of these on the radar. Well, we did see ice shelf disintegration, but not very much of it. Now on the Antarctic Peninsula, 7 out of the 12 ice shelves have disintegrated, either completely or partially. So, and that's happened over the last 15 years. So this is all decade and a half kind of discovery. And we hadn't been looking at the ocean heat at all. Had totally underappreciated that. And so my summary is that simple 4 words: ice sheets hate water. I've been wearing it. You've been learning it all along. And we're getting better. I mean, this is job 1 for us. This is where the work is focused, and we're making progress. But as this audience well knows, science can't. The pace of scientific understanding and knowledge can't often just be bought with a bigger check, but it can be facilitated that way. But we've got focus, and we have more glaciologists now. It's actually it's a lot of fun. So with that, I'll pause and stop, actually, and ask for questions, and I'll start here. So thank you for your attention. I hope you enjoyed. Sure. Some URLs if you're URL starved.
Talk about 1 meter sea level rise. What's your baseline? Is there like since 1950 or?
Turn of this century. I mean, 1990, 2000.
Okay.
That's a
over
baseline.
The course of this century, we'll get
Yep.
a meter of rise.
An extra meter. Yep. Yep.
Hi, Bob. You spoke about the contributions to sea level rise from ice sheets, but can you talk about a little bit about the ocean expansion just to global warming, and what magnitude or what percentage of that 1 to 2 meters it represents? Yeah. So the question was how significant a contribution is the thermal expansion, and how might that change over time? If you go back to sort of the first IPCC reports back at the end of the previous century, sea level is going up about 2 millimeters per year, and half of that was due to thermal expansion. That basic contribution, so about 1 millimeter per year from just expansion of the existing water in the ocean. That number hasn't changed over time, and people don't expect that to change much over time. It may increase slightly.
So when you look at the 3.1 millimeter per year, or even the 3.8 that you can find in the literature, that 1 millimeter per year from thermal expansion is about a third. So its proportional contribution is decreasing simply because the ice sheets and glaciers are contributing an increasing rate. So it's still important. It's not a small wedge in the pie, if you will, but it's decreasing over time. Yeah.
We'll take one more quick question.
And I'll stay around.
From here, any question?
Yeah, I had a question about, did you notice any effect from the Iceland volcano? Did it make the ice sheets? I realized you could cut down on sun, but it also could have darkened the ice.
Yeah, it would be minuscule. I mean, you look at any single glacier, and it's not contributing much. It really is the aggregate of everything that's going on. And there's a lesson to be learned in that. I mean, we can go to a glacier to study a process. We can't go to just today's hot spots and expect to get, and to sum up their contribution and expect to get the whole answer. It's a very episodic kind of behavior. So those big explosions that I had in Greenland, I mean, some of those have quieted down. Others have accelerated. So they each have sort of their own unique drumbeat that on which they'll spurt. If is not a good term, but then you aggregate that and you get actually a much smoother increasing.
The thought came when you talked about the change in the crustal dynamics, which is going to increase volcanic activity, etc.
I would say that feedback is totally unexplored. I don't know of anyone who is actually looking at that particular aspect, and it may be important. I mean, this has sort of been a career full of surprises for me, and I don't anticipate we've experienced all those surprises and made all the discoveries. There's a lot more to be done. So, yeah.
Let's thank Bob once again.